the thing we need to do at first is we need to sort of summarize where we've been and what exactly we're actually trying to do. So here is the summary of the last few classes. So the first thing is we had a question. And that was given a curve, y, a max and or min value. And what this led to is this led to us kind of learning a bunch of new stuff. So this led to new definitions, such as global and local extrema, increasing, decreasing, concavity, etc. So I'm not going to list all the terms, but things like critical numbers, global, local extrema, increasing, decreasing, etc. So we started all this off by saying if we have a function and if we look at its graph, does it have a maximum? Does it have a minimum? And then we said, well, okay, let's define these terms because they're descriptive of what a curve looks like. And then we thought, well, how can we verify or how can we reason what the picture shows us? Or even if we can't necessarily know what the picture is, how do we reason the shape of a graph? And more generally, how do we reason the characteristics of a function using calculus? And so once we made these definitions, we were able to reason. So we stated theorems to help us reason what characteristics a function has. And what were some of these theorems? Well, there was the mean value theorem. And then we had this thing called Fermat's theorem. And then we had the first derivative test for extrema. And we had the second derivative test for extrema. So, and of course there were other theorems, but these are the big ones. And so if you're looking for a resource other than what we've talked about in class, I mean, the specifics of all of this is located in the first 3 sections of chapter 4. So all of this is in sections 4.1 through 4.3, I think. Yeah, 3 in our book. So again, this is essentially a recap. These first 2 pages that we're writing on now, these are essentially a recap of what we've been doing the last few classes. So what I thought we could do is I thought we could actually do an example or two to show all of this, and then we'll start sort of going in another direction. Before we do that, does anybody have a question or a comment? I mean, you don't have to say anything. I'll just assume you're all sleeping. I'm just kidding. Is anybody even showing? No one's showing their faces. I don't blame you. I wouldn't show my face either. I sort of have to, though. But I'm not even looking at your faces. We'll just pretend you're all sleeping, or actually, I'll pretend you're all really, really paying attention. Okay, so let's do some examples that are going to help you for your next homework. By the way, I'm going to post 2 homework assignments. One is math and the other is a writing assignment. So hopefully you can do both of those for next week. But anyhow, these examples we're going to do right now are going to be useful for the next homework I assign. So here we go. This is sort of a culmination of everything we can do now. Let me spell this correctly because it looks suspect. So this will be our first one. So I want to suppose that I have some function. In particular, it will be 1/3 x cubed minus, I don't know, let's think of a good thing that will work out in our favor so that we can make sense of everything. So how about 625x? So here's what we want to do. We want to do the following. We'd like to determine the following. So the first thing we want to determine are critical numbers. Why do we care about these? That we care about these because these are the candidates for any local extrema. We would like to determine intervals of increasing and decreasing. We would like to determine intervals of concavity. We would like to determine any extrema. And then determine any asymptotes. And then the last thing we would like to do is sketch the graph. So this is sort of what we want, we'd like to do. So again, like I said, I'm going to post these whiteboards to Canvas later, and I'll upload this video as well. Although, even though I'm going to do that, I would encourage you. I don't know. I think, maybe I'm full of what, but I'm of the belief that if you write things down, it helps you to remember them. So what I mean by that is I'm of the belief that taking notes is the way to do things. And I'm not saying you have to, but that's just sort of the way I'm encouraging you to go about this. Anyhow, does anybody have a question about what we're being asked to do?
No.
Yeah, I like that. Just say no. Now I know you're alive. This is good. Okay, now here's an interesting thing, and this is going towards the things I've complained to you guys about before. I'm going to share a different page with you, so I'm going to share Desmos with you, and hopefully you're all seeing Desmos. And I want to graph this in Desmos, so I'm going to just do what I think I know how to do. That is f of x equals 1/3 x cubed, and then this is minus 625 x. And when I graph it, it looks like a straight line. Now, if we are using any of our previous attained or obtained knowledge, what you should be thinking is something ain't right, because you should be thinking, I studied polynomials and their graphs in algebra class, and excuse me, you should be reasoning, okay, something's not right, because I know that this thing looks, at least it should have some sort of shape. And when I zoom in on this or I zoom out on it, it looks to be a straight line. Oh, and then we zoom out and now it doesn't look to be a straight line. It looks like we have 3 straight lines. So it's not clear using sort of Desmos, which is pretty good software. It's not clear exactly the shape of this. And if we zoom out, now it looks like we have one big line. So we think we know what this creature should look like by what we learned in algebra, but it's hard to tell what's happening on Desmos. So what we're going to do is we're going to just say, okay, this function, probably by the way it is designed by the instructor, is hard to graph using software. Now, of course, if we were using our brain a little more, we might say, oh, well, let's just go up here and let's change our axes. Maybe we say, okay, it looks like it's between -100 and it looks like it's between 100. And then who knows what's happening down here? How big is this creature? Is it like negative, I don't know, 1,000? Is it between that? So again, this is not efficient, me taking guesses and checks to see what the shape is. Although once I zoom out a little bit, I start to see that it does have a familiar shape. But we have an option. Instead of having to sit here and play this guess and check game on the graph, what we can do is we can do quick and swift analysis using the tools we learned in calculus. So instead of going through all this trouble, we can do this and we will know what the graph looks like. So does anybody have a question, comment? I'll get a sip of my, look, even though I'm at home, gang, I still got my Rockstar. They should pay me. This is good advertising for them. And Yeti too, overpriced water bottle cups. All right, good. So let's go to the next page and let's do this. So here's my advice on how to do this kind of stuff. We'll make our A like this. My advice is to compute f prime and f double prime before anything else. Because we know those are the two players. Those are the guys that hold the information. So f prime of x is x squared minus 625. And we know that this creature, because I chose it that way, this guy factors quite easily. This is x minus 25 times x plus 25. And then over here, the second derivative is just 2x. So what's nice about this is right away, I know what my critical numbers are. So the critical numbers are solutions to f prime equals 0. So we know x equals 25 and x equals negative 25 are the critical numbers. Also known as the candidates for extrema. So if you go back to the previous page, you'll see that we've answered part A. Okay, so once we do that, the next thing we need to do is make sign charts to get our intervals of increasing and decreasing, and our integrals of concavity. So that's what I'm going to do. So for f prime, there are two places where the derivative changes sign. It can change sign at minus 25, and it can change sign at 25. So the way I told you guys I like to do this is I'll make a sign like this. And I need to pick 3 points. The easiest one for me to pick is the one in here, because I'll just pick 0. And when I plug 0 in here, I get negative 625. And that's negative. So what I'll do right underneath there in red is I'll put on this interval, this is decreasing. Not to change the subject, but you might have noticed that I just went like this. And it's because Amazon is at my house delivering me something. And I was like, why is it so loud? And they are bumping some music. It is great. What a time to be alive. My house is legit like thumping. I should give you guys a tour of the house, although I don't know, because I don't know you guys well enough. I could say like, because like right now, what are we doing? Right now, what do I have, like one of those backgrounds, right? Is that what I'm doing? Yeah. Actually, I can unleash that and show you what's behind me. Okay, anyhow, let's get back to math. Now, the next thing I want to do, I'll pick a different color so it's a little more clear. I need to pick something over here. So I'll go right ahead and I'll pick f prime of 26. And then like I told you yesterday, or excuse me, Friday, I think, or Thursday, you can plug 26 into this expression, but it's easier to do it down here because the arithmetic's easier. So when I plug 26 in here, I get 1 times some positive number. So if I just write this, this is 1 times 51. right, which is clearly positive. And so we know that we're increasing on this interval. And then similarly, what I'll do over here, because it's going to be very very similar to what I just did over there, I'm going to pick negative 26. And when I plug that in, I'm left with negative 51 times negative 1. And of course, that is positive 51, the same thing I got here. And so this tells me I'm increasing over here as well. Now, another thing that it's worth pointing out is as I get a freebie from this table tells me even more. So let's remind ourselves that this table also tells us the following. So we conclude F is increasing on, and here's the correct way we'd write this. We write this negative infinity to 25. And then we use this union symbol, which I don't know if any of you are familiar with, but if you're not, that's the correct mathematical notation. So it's increasing there, and it's decreasing on, hold on, I have a typo here. This should be minus 25. So that's what that table tells us, but it also tells us then by the first derivative test, we have a relative max at negative 25 and a relative min at positive 25. Any questions or comments? Okay, so we can write that down as well. So we also conclude F has a relative or local max, whatever adjective you want to use, at x equals negative 25, and a local min at x equals positive 25. So a couple things you'll notice is I'm taking my time, and what we're really doing, I'm going slow for one. Well, maybe you don't think I'm going slow, but I'm going slow. And I'm being thorough. And this does take some time, even if I wasn't. We're really analyzing the function. So if you have a comment or a question, please speak up. So now let's repeat. Oh, that's bad. We're going to repeat for the second derivative. So if I make my sign chart, the only place the second derivative changes sign is at 0. Remember, the second derivative is 2x if you're keeping score at home. And so clearly when x is, this should not say x here, by the way. It should say 0. When you're over here, say f double prime of 1, you get 2. That's clearly positive. F double prime of negative 1 is equal to negative 2. That's clearly negative. So this tells us we're concave down, and we're concave up over here. So that's what we conclude. We conclude F now is concave up on 0 to positive infinity, and concave down on negative infinity to 0. So what's nice is we have now answered, if you go back here, we started by asking, can we do this? And we've answered A, B, C, and D so far. What about E? Well, there are no asymptotes because we have a polynomial. So our original function is a polynomial. There cannot be any asymptotes for polynomials. So we can now graph this thing. So it might be worth pointing that out. So we are ready to graph. And note, since f is a polynomial, it doesn't have asymptotes. So if you have a question or something, please speak up, or don't, whatever you want to do. All right, so how do we graph this? Well, so before graphing, we should compute some important points on the curve. For example, you might want to get the y-intercept. The y-intercept is what happens when you plug 0 into the function, and when you plug 0 in, you get 0. And that tells us that 0, 0 is on the curve. What about the x-intercepts? Well, these are solutions to f of x equals 0, which is 1/3 x cubed minus 625x equals 0. Which one way you can solve this is you can factor out an x. But you can also, okay, let's just stick with that. Factor out an x and you're left with 1/3 x squared minus 625 equals 0. So you get 3 of these. you get x equals 0. And then x equals, well, you're going to get a square root, 2 of them, because if you solve this, if I solve 1/3 x squared equals 625, well, that's the same thing as taking 3 to the other side. So if you just do a little bit of algebra, whether you do it on paper or do it in your head, I don't care. 625 times 3 is 1875. Let's double check. Yeah, 1875. So this plus or minus the square root of 1875. Which, of course, you can approximate with a decimal to get an idea of where it's at. So that's approximately 43.3. So it's plus or minus that. Now, before I finish this, let me point something out. I am saying we can do this. I am not saying this is the most efficient way to graph something. I am just showing you what we can do with the math. I can do all of this without even looking at a picture. And I'm going to be able to create the picture just doing all this. Okay, so the last thing I'm going to calculate before I sketch the graph is I would like to know what the extrema, the output is at the extrema. I know I have a min somewhere. I know I have a max somewhere. I'd like to know the output at those two things. So I'm going to calculate the value of f at the extremas. So we need to know what is f evaluated at -25, and we need to know what is f evaluated at +25. So this becomes -1/3 times 25 cubed, because it's 1/3 x cubed. And then this is minus 625 times -25. Now, what's nice about the way this works out is 625 is 25 squared. So this is actually not too difficult to do by hand. You know, you're left with -1/3 times 25 squared. And then this is plus, 25 cubed. And a negative is plus, so this becomes plus 25 cubed. And so another way of writing this is 2/3 times 25 cubed. So what I'm going to do is just check my arithmetic, because that would be bad if I didn't. So using the same reasoning over here, this would be 1/3 times 25 cubed minus 25 cubed, if you use similar reasoning. And so this becomes -2/3 times 25 cubed. So if you do the math, here's what you end up getting. So the max is negative 25 comma. If I compute this number, what I end up getting is I get 31,250 over 3. And the min is let's maybe write that over here so it's clear. It's very symmetric. It's 25 comma negative 31,250 over 3. So a couple things that I think are important for me to point out to you is notice I am not using any approximations. I'm using exact values. Does anybody have a question about this? Comment. All right, so now I can put everything together. So here's how I think I would like to do it. If I'm sketching this to be representative, I'm gonna first take my XY axis. I'll make it nice and big. Now I'm going to draw my axes at different scales because as we saw at Desmos, the only way to really see what's happening is to do that. So the first thing I'm going to do is I'm going to mark down some important points. So for example, I know that I cross the x-axis. So if you go back, so I know I intersect the x-axis here. And then if I go back 2 pages, I know that I also intersect roughly at 43 and negative 43. So probably a good thing to do is to maybe think about this as being 50. And then that means I intersect somewhere here. And then also why 50? Because at 25, we know we have a min. And then I'll do a similar thing over here. I'll have negative 50 and then I have 25. And then I know that I intersect somewhere here. And then I need to make my vertical scale so that this thing makes sense. So perhaps I'll put something like, I'll make this, I don't know, say 10,000. And then down here, I'll have negative 10,000. Now, why am I choosing that? Well, because I'm choosing these values because if I go to the previous page, I know this number, say, for example, this number is slightly bigger than 10,000. How do I know that? Because I know 3 is going to go into this a little more than 10 times, particularly 10,000 times, at least 10,000 times, I should say. So what I can now do is I can now reason using my calculus what happens. I know I have a maximum here. And by the way, that's negative 25. So let's fix this. And I can even be very specific. What is my maximum right here? Well, we found it on the previous page. It's negative 25, comma, what was it, 31,000. 250 over 3. And then I know I have my minimum right around down here. And this guy is positive 25, comma, 30, negative 31,250 over 3. And so what I can do is I can now use the calculus to connect the dots. I know that I'm concave up and I'm increasing. So my graph's going to have to look something like this. And then this guy has to come down like this. And then go back up. And since it's increasing, it has to go like this forever and ever and ever. And so now I have a more accurate representation of what this function's behavior is. Does anybody have a comment or a question about this? Okay, so here's what we can do. Now we can go visualize this on Desmos. We can sort of move our scale around. So we know sort of what our scale needs to be to see sort of what's happening. Our x-axis should be between something like negative 50 and 50. And there you go. So that picture is very much similar to what we just did. And by the way, you can see more exact values here of your max and min. And even the x-intercepts. All right, does anybody have a comment or a question? By the way, again, for those of you who weren't in class Tuesday, you know, I understand this is a polynomial and I could have, you know, it seems like I just spent a lot of time doing extra work when Desmos figures it out for me, or maybe other software. But I do need to remind you that that's not always the case, because this is a polynomial, which in the big scheme of things are the most basic of all functions. But there are many, many functions out there that the software just can't graph, at least not yet. And we need to be able to do some analyses or some analysis in order to make things work. But anyhow, hopefully you will be able to do this. And again, on the next homework, you're going to be asked to do this for a few functions. All right, so let's look at another important example that might be familiar to some of you. Before we do that, though, does anybody want to ask a question or a comment? I'm actually pretty happy with this graph. I don't think it's that damn bad. See, when I was in calculus years ago, we used to have graph paper and we had to have these meticulous graphs. Of course, back then, there wasn't things like Desmos that were free. Okay, so let's move on to another problem. This one's actually on your homework. We'll see how many of you get it correct. So our second example is the following, and I'm not going to write all that stuff down. What I'll say here is I'll say analyze, and you can put the details in, but I'm going to do most of the work for you. Analyze and graph f of x equals e to the negative x squared. So this guy is perhaps one of the most important functions that exist. Ironically enough, and I think I've pointed this out, but this is one of the fundamental functions in the study of statistics and probability. And what that means is that this, believe it or not, the graph of this function affects your lives in ways you would never really think about, from interest rates to loans to all kinds of certain things. And you might understand why when we're done, and then I'll sort of yap about it. So here's what we'll do. What we'll do to analyze is we'll start by computing f prime and f double prime, just like we did in the previous problem. So f prime of x by the chain rule is negative 2x e to the negative x squared. Now, the second derivative, we have to use not just the chain rule, but also the product rule. So what I'm going to do, and this is one that usually frustrates us, it's a little difficult. I'll think of this as my first function, and then this is my second. And then I'm going to recite in my head sort of what I told you guys to do weeks ago. You take the derivative of the first, which is negative 2. Leave the second alone, plus the first times the derivative of the second, which is the same thing as we started with, or our first derivative, I should say. And so this thing actually cleans up. It looks frightening, but it's really not that bad. I can pull e to the negative x squared out of all the pieces, and I'm left with negative 2 plus 4x quantity squared. So I can clean this up. I can pull out a 2. I'm left with 2e to the negative x squared. And then this is 2x squared minus 1. So this second derivative is, it might take you a few tries for you to make sure that you got it correct. So if you have a question, please let me know. All right, so very good. So here's the thing to note, and I said this last week, or maybe I said it again on Tuesday. I'm going to repeat it again because you have to know this. So here's an important fact. E to the x is always positive. Always. So thus, even e to the negative x squared is greater than 0. It's never equal to 0. You could spend the rest of your life going to a calculator or doing it by hand and taking e to a negative of a number squared. It's just never going to be 0, and it's never going to be negative. So what that means is we can make conclusions from these derivatives. The first derivative tells us we only have one critical number. So this fact combined with these equations tells us we have one critical number. That's it. And the second derivative equals 0 twice. So it's worth writing that down. So we have one critical number. X equals 0. So we can make a sign chart. And if I evaluate my first derivative at, say, -1, when I get that, I get +2 times e to the -1 squared, which is just -1. This is positive. So we're increasing. And then when I plug in 1, I get -2 e to the -1, which is negative. And so we're decreasing. So f increasing on -infinity to 0, and decreasing on 0 to infinity. So again, I pointed out to this idea twice, that even though this is e to a negative number, don't forget that e to the -1 is just 1 divided by e. It's a positive number. Okay, so what about the second derivative? The second derivative, which I will remind you, is 2e to the -x squared times 2x squared minus 1. This guy equals 0 when x equals plus or minus, solve this, 1 over the square root of 2. So we can make a sign chart for that. -1 over root 2, positive 1 over root 2. And just pick some test points. What's f double prime of 0? When you plug that in, you get a negative number. It's actually -2. Put something bigger in. How about plug 1 in? When you plug 1 in, you get a positive number. And if you plug -1 in, again, it doesn't matter what number you plug in, or excuse me, what the output is. All that matters is that it's positive. And you can actually see that. If you plug 1 in here, this is positive. You get 2. And so this is 2 times a positive number, which is positive. So what do we get? We get f concave up on -infinity to -1 over root 2 union 1 over root 2 comma infinity, and then f concave down in between. Now, here's what's interesting, and I'll share that in a moment. Does anybody have a question? Comments? So either one of these pictures verifies, either this picture or this picture, they both verify that there is a maximum at x equals 0. And it has to be global because of the increasing and decreasing. So we conclude F has a global max at x equals 0. And if you plug that point in, what's that point? That's just a point 0, 1. And what's more importantly, F has no local mins. None. It can't have any. And how do I guarantee that? Well, there's only one candidate for extrema, and we found it. Not only that, we know we're decreasing on from it, and we're increasing up to it. Now, there's only one more piece of information we haven't used, and so using this fact that we talked about back in chapter 2. So using the fact that the limit as x goes to infinity of e to the negative x squared, which is of course the same thing as the limit as x goes to infinity of 1 divided by e to the x squared. So using the fact that this equals 0, and of course, for the same reason, if you go to negative infinity, this happens. We can sketch the graph. So here's our horizontal axis. Here's our vertical axis. And here's what we know just from our analysis. We know the graph has to go through the point 0, 1, and this is in fact a maximum. It's global. We know that at 1 over the square root of 2, concavity changes, and then we know at negative 1 over the square root of 2, the concavity changes. So with just that little bit of information, here's what we know. We know that this creature looks like this. And we have asymptotes. So maybe you might remember this from some statistics or some other class, but this is the famous bell curve. Or some of you might know it as the normal distribution. So if you ever took a prob and stats course, there's no doubt that you had to, at one point you did these problems where you either used a calculator or you went in the back of your book and looked at, they called them z-score tables. And what you were doing is you were looking at numbers that happen to be the area under this curve. So this turns out to be a very important function. And it should be pointed out again, like I said, these are asymptotes down here. They never cross the x-axis. Oh, hold on one second. Things about to die. My computer was unplugged. All right, so one of the things to note is we can go graph this real quick. And if we do that, we get what I just drew, the old bell curve. Okay, does anybody have any comments or questions about this or the other two problems? So what's we spent about we spent about almost an hour working on two problems. So you can see that these things are tedious, but they are, I mean, you can definitely go faster if you wanted to. Okay, does anybody have a comment or question? All right, well, listen, I will wrap it up then. I'm gonna stop now. I will upload this stuff later to Canvas, and I will hopefully see you guys in person tomorrow. Like I said, what I'll probably do, what I'd like to do is hopefully we still have people show up in person. And as long as people continue to show up in person, we will also try to maybe do classes like this live so that those of you who can't make it can have something to read at a later date or watch live on Canvas, not Canvas, but Zoom. All right, guys, thank you very much. Show me an email. I know a couple of you emailed me. I believe, yeah, Carly, you're here. So I will get back to you. I know you emailed me the other day, Carly, and I think, did anybody else email me? No, not that's in here. Okay, so I'll get back to you. Thank you guys very much and take care. I will hopefully see you tomorrow. Bye.